Hello friends, welcome back to our channel EASI. Everything about semiconductor industry or everything that you need to know about semiconductor industry. Today we are going to talk about EUV lithography. So let's get started. Lithography is one of the most critical steps of manufacturing. It is the process that prints billions of microscopic transistor patterns onto silicon wafer. Each generation of chips demands finer and denser patterns, and the precision of that printing step determines a chip's speed, power efficiency, and cost. Following the Moore's law, every 2 years chip makers have pushed transistor counts higher and higher, a pace only possible because lithography kept resolving finer and finer features. Why wavelength sets the limit? The smallest feature a lithography system can print follows the Rayleigh criterion. Shrinking the critical dimension, that is the CD in the below equation, means shrinking the wavelength of light lambda or pushing the numerical aperture of optics as far as it goes. We started with I-line, which was 365 nanometer of wavelength. Now we are talking about EUV, that is 13.5 nanometer, which is 14 times shorter than DUV, which it is replacing. Before EUV, chip makers stretched 193 nanometer light far past its natural resolution by exposing each layer multiple times using spacerization technique. Thus, the cost was high, the complexity and error was even higher. With EUV, it requires single exposure per layer, thus simplifying the flow and making the overlay much tighter. We talked about the advantages of EUV lithography. Now let's talk about the challenges. EUV sits at the boundary of the soft X-ray band. It is absorbed almost instantly by glass, air, and most of the materials, which is why every part of the system built around it had to be reinvented. It is absorbed by glass, thus lenses cannot be used. All optics must be reflective mirrors. It is absorbed by air, thus the entire light path has to run in ultra-high vacuum chambers. And as it is absorbed by most of the materials, every surface and particle in the path steals usable photons. Now let's talk about the light source. Every UV scanner manufactures its own light using a process called laser-produced plasma. A molten tin droplet about 25 micrometer is fired into the vacuum chamber. A laser pulse is sent to flatten the droplet into a disc to improve coupling. Then a high-power CO2 laser strikes the disc, heating it into a plasma. That tin plasma reaches to the temperature that it radiates UV light. Each droplet is struck around 20,000 to 50,000 times per second to sustain a continuous source of usable UV light. Because UV is absorbed by glass, every lens in the system is replaced by a curved mirror coated in a molybdenum silicon multilayer and dozens of alternating atomic scale layers tuned to reflect one specific wavelength. Each mirror reflects roughly 70% of incoming light, and the scanner's path uses 6 or more mirrors, so losses compound quickly from source to wafer. The photomask itself is built on the same multilayer mirror stack. A patterned absorber layer sits on the top. The exposed mirror region reflects UV onto the wafer, while the absorber blocks it, printing the circuit pattern. Because light strikes the mask at a slight angle rather than head-on, even a single nanometer scale particle on its surface can cast a fatal shadow, making mask defectivity one of the UV's hardest problems. As UV light cannot travel through air, so the source, optics, mask and wafer all sit inside ultra-high vacuum chamber. Keeping that environment clean is a constant battle. Each plasma pulse sprays microscopic tin residue towards the collective mirror, gradually dulling its reflectivity. Thus, a continuous flow of hydrogen gas reacts with deposited tin, forming a gas that is pumped away to keep mirrors clear. A single stray particle on a mirror or mask can print as a repeating defect across every wafer exposed. UV photons, though, carry far more energy than DUV, but far fewer of them land on each square nanometer. That randomness or short noise makes it harder to print a clean and repeatable edge. Thus, resist designers have to balance three properties that pull against one another, and it is called the RLS trade-off. Finest feature the resist can define, called the resolution, smoothness of the printed edge, called the line edge roughness, and the dose of light needed to expose it, called the sensitivity. Improving one without a chemistry breakthrough tends to cost the other two. The next step in UV widens the numerical aperture. From 0.33 to 0.55, the sharpening resolution enough to reach sub-nanometer level logic nodes. However, high NA UV comes with the challenges of asymmetric magnification, smaller field, thus more exposure or more stitching. The trade-off of finer resolution comes at the cost of throughput and added stitching complexity between exposure fields. Though no single company builds the UV scanner, but the final assembly is made by only one, that is ASML, thus making the entire supply chain a strategic choke point in global chip making. So to summarize, UV lithography turned a decade-old physics limit into a solved engineering problem. Tin plasma light sources, atomic precision mirrors, reflective masks, and resist chemistry all working together at nanometer scale. It is one of the most demanding manufacturing processes ever built, and it now sits quietly at the center of nearly every advanced chip in the world. With that, we have concluded our today's session. If you liked it, please like, share and subscribe. See you next time. Till then, stay safe and stay healthy.